But if it doesn't move to the project, we will start the days. Let us know. I'll see it.
Okay, let's start. Because we don't have that much time left. Surprisingly, the semester is coming to an end, so we have to hurry up a little. So the plan for today is the following. So we'll finish discussion of the context switch, which we started last time. I will go over it again just to make sure that everyone is on board and remind everything. Then we will come back and I will explain how we create the first process. Just because when we started talking about the context switch, we already assumed that the process is running, right? And we said, okay, we exact at some point, right? And then the timer interrupts are coming and stuff like that. And then I hope I will have time and I will explain how the system initializes other CPUs, because up until now we were always discussing just one single CPU. But in practice, x86 is capable of running multiple CPUs like any other operating system, right? Quick announcement. So we moved the deadline for the homework to Thursday, just a couple of days, but I cannot move it further just because I want to assign yet another homework. It will not be super hard, but again, it's a little bit tricky. So it's extending x86 with threads, right? Okay, back to this. So remember how it goes. So we were running in a user process. Let me just quickly. Running something here. We had our stack here. We had a SP register pointing here. EBP is here. If we maintain the stack frame, which is like not enabled by default, but x86 supports it, right? So we're doing this. So then suddenly the hardware says, okay, there's a signal, right? So there's a physical chip on the CPU, which periodically sends you like an electrical signal saying, okay, like this is an interruption. The pipeline of a CPU reacts to it, right? And what it does is that it says, okay, I understand that it's a vector 32, so I will follow this protocol. And the protocol which the hardware follows is that it says, okay, I will go ahead and take a look at my interrupt descriptor table register, IDTR, and whatever the operating system put there. By the way, it's a virtual address, right? So if suddenly if suddenly the CR3 register is not configured correctly, you just fold right there. You do a double fold, and then the second fold is not coming through. You do a triple fold, and at this point, the hardware reboots, right? And this is what you've seen on like your previous homework, people. Unless you set up the page table correctly, the moment something happens, you get a triple fold, just because you cannot even handle an exception, right? Although the QEMA was showing you that, okay, the exceptions are coming in this order, but we just don't know how to process it. So, okay, so it translates the virtual address of the base address of the interrupt descriptor table through the page table, gets a physical address somewhere over here, and then says, okay, look, I'm gonna read the entry. And it knows that the hardware sent like interrupt number 32. So it reads the entry 32 because it knows the hardware knows the sizes of those entries. It treats this table as an array, reads entry 32, and reads specifically like there is some bits which control the privilege. Interrupts from hardware can only be disabled through the eFlags register, right? But so if or like interrupt flag is set, then it's enabled. If not, it's disabled. And so if it's enabled, it reads these two things. It reads the code segment, which says, okay, I will choose a new entry in the global descriptor table. So for that, the hardware goes ahead and reads the GDTR global descriptor table register. Again, it's a, well, I say virtual, but okay, it's linear address or virtual if you like. Again, does the translation. If everything is fine, figures out this table, reads whatever the entry the operating system puts there. So in our case, it's entry number 1. From here, it reads a new code segment. So essentially switches the privilege level from 3, if you were running at privilege level 3, you switch to 0, right? And what it does, it says, okay, that's totally fine. I can also read the address of the interrupt handler here, which operating system configures, again, virtual address. But in order to run this handler, the hardware needs to save these 5 things on a stack, right? And since we agreed that, okay, it's unsafe to save them here because this value of the ESP register can point anywhere, right? And the user can set it up to actually overwrite, for example, one of those tables, right? So the hardware says, okay, I need a new stack. And it goes ahead and figures out the TSS table. The way it's done is that there is an entry in the global descriptor table which points to the TSS, and there is a current segment. I never talked about it maybe. So it's a task state segment, right? So it's again register which was loaded similar to code segment. So it just chooses the entry in the global descriptor table, and here there will be a pointer to this task state segment. From this task state segment, we read this stack register and a stack segment. So stack segment again points us to the global descriptor table, but the stack register points us somewhere over here, and this is where this stack is located, right? At this point, the hardware says, okay, I'm ready to go. It seems like there will be no crashes here. So it saves these 5 things on the stack and jumps to the execution of this interrupt handler, right? Just again, like, this is related to your homework, just because you are asked to extend the x86 with yet another system call, which is implemented as an interrupt. Instead of 32, it's implemented with interrupt 64, I believe. So it's X40, right? Any questions about this diagram, which I keep coming back to this diagram, hoping that at some point everyone will start believing me and understands how it works.
Currently, you're showing only one process, right? So one stack is user and another stack is kernel, right?
Yeah.
So let's say we have another process and we create one more stack and also kernel stack, right?
Correct. So each process will have its own private kernel stack. And we will be doing this context switch in a second. We'll come back to it. We will be switching those stacks between as part of the context switch.
But where do we store those, all those information? I mean, do we store it in TSS? Let's say we have a 2 process and...
No, the way it works is that, I will come back to it in a second. So each process in the kernel is represented as a proc data structure. This proc data structure has a k-stack pointer. So when we allocate a new process, allocate this new data structure, as part of it, we allocate a new kernel stack for this new process. And then we store it here. And since this, essentially when we context switch, we'll be loading this value in the TSS. So we not going to create, multiple design choices are possible. And it's arguable which one is the better. But the thing which x86 does, which essentially just changes this value of the TSS every time it switches between the process, seems like a reasonable approach. Good? Anything else? Okay, so, and what we started doing, we started descending down this interrupt path, right? So vector 32, we push the interrupt number, so later on we can dispatch on it. We go into the all traps essentially saves everything, all the segment register on a stack, saves all the general registers on a stack. It switches the kernel data segment. At this point, you can start using like a move instruction, because up until now, only the stack segment was set by the hardware from the TSS, right? So I'm not 100% sure, but I assume if you try to do a move instruction here, you will crash, right? That's my hope, because the data segment is still set to be to point to the user entry. So it's a good, like, change it to a move relative to the ESP and chat. Whoever does it, I will give some extra credit for this and explain the crash, right? But on QEMU. By the way, QEMU has bugs. It's not surprising. It's a complicated piece of software which emulates the hardware. So if you take, for example, QEMU VirtualBox, which also uses QEMU, But let's imagine you have some other emulators like Box. There's another one, Box. And you compare them, you can find bugs by just comparing the outputs, right? So it's called equivalence testing. And at some point you say, look, QEMU reacts slightly different to this specific corner case. And then you can figure out that one of them has a bug. So you don't know which one, but then you inspect, right? So that's not surprising, but okay. Reasonably it's good, but some people do search bugs, do find bugs in QEMU. Okay, got it. Sorry for this detour. Then you say, okay, like I'm tired of running assembly. So you're pushing this, the data structure, which we formed on the stack. We call this data structure a trap frame. And you say, look, I'm gonna push this trap frame as an argument to the trap function because it actually takes the trap frame as a pointer. So you push the current value of the SP as on the stack itself. So you have a data structure like this on the stack, right? At this point, you are adhering to the calling convention. So because the first argument is on the stack, you call a function which takes this first argument, and you're ready to go and see, right? So this is how your stack looks like, right? So you call this trap function increments the ticks, and then eventually says, okay, yeah, time for me to yield. Essentially, the tick has passed one. We were running already for one single interrupt. It's not true actually in x86, because in x86, maybe you just a millisecond ago, you just switch into this process because someone else yielded. And this process was running for only this tiny millisecond. And again, the timer interrupt came. And you lost your slice. So there is no real fairness here. So it may happen that, like, I guess statistically it's fair because it's like each process probably will get an equal slice, but like a real kernel would do like a more fine-grained accounting of how much time the process was running, can account for that and say, okay, you were running for only 1 millisecond, so maybe it's fair for you to run for a little bit longer next time, right? Okay, and then it invokes this funky thing, the function which is called scad. And what happens here is this function itself invokes a magical function which is called switch. So switch is a function which is implemented in assembly, and conceptually takes two arguments. One argument describes where you're switching from, and the other one describes where you're switching to, right? And I was pushing this analogy of two boxes. So conceptually, this is a pointer to some kind of a stack, right? So there is a stack, and this is the pointer to the top of this stack. And on the top of this stack, we form a data structure, which is called a context, right? And the switch knows how to restore the state of this process from this context. So this is our box, right? And the second argument is essentially a pointer to a variable where we're going to save the location of the current context. So again, if we have a current stack, we will save everything here on the very top of the stack, right? And this variable context, it will be a part of the proc data structure, right? So this is what we do. So we have a proc data structure, and it's a field of a proc data structure, and we're passing a pointer to that field. So this field is called context, and we're passing the address of this field right here, right? And so what we're gonna do is we will essentially establish a pointer like this. So essentially saving where are we switching from? We packaged everything and saved the location of this package, right? Inside the proc data structure. And the switch will switch to this new context here, right? This is what we were doing last time. Does that ring a bell? So do you understand this figure now? Right, so we saved everything. Okay, cool. Okay, so this is what we were doing. And then we did a tiny detour saying, okay, so what's important here is that the switch function saves only what? Do you remember what is saved inside the switch function?
Caller, still caller register.
Which registers?
Except the EDI, SI, except those remaining ones.
Right, so we only have to save the callee registers, right? because everything else is already saved. So for example, if, for example, whoever calls the switch functions cares about the value of the EAX register, for example, it will push the EAX on the stack. Maybe it will not, because maybe it doesn't care. Maybe the caller of the switch doesn't care about EAX at all. Then it gets unsaved, and it was saved somewhere earlier, right? But what the switch is doing, it says, okay, according to the calling convention, we only have to save the calling saved registers, right? And there are not many of them, so only 5, right? And this context data structure is essentially defined in such a manner that if you set up a pointer to the top of the stack, it will match the layout of this context data structure. This is how we push it, right? So at the very, we first push okay, hold on. So we push EDI here. So the memory grows this way. So this is the max address, and this is the 0, right? So you have a pointer. So EDI will be on top, then ESI, right? And this is what we pushed here. Then there will be EBX, EBP, and then EAP is saved when we call the switch. So EAP is actually part of this data structure, but it was saved not as a part of the switch function, but as part of the call instruction, which called the switch, right? Okay, cool. And so, and then there's 2 arguments which we use here, the caller save registers, right? So if caller needs those registers, caller already saved them, push them on the stack already. So we find to essentially move them from the stack to the EAX and EDX. And then we just essentially initialize ESP with the value of EAX. And we saved the old value. Hold on, the other way. So it's a GNU assembly. So essentially, you save the value of ESP into the pointer. This is like in Intel assembly, you would write it like this. Sorry, move EAX ESP. So the value of the ESP gets saved into the memory address, which is pointed by the EAX. So if there is some kind of a memory which is pointed by the value of EAX, this is where the value of ESP is saved, right? So this is the context field. If this is the prog data structure, this is your context field, right? And on the opposite, so here you say, look, the context which was passed to me as a second argument, I will initialize it. I will move it into the stack, and my new stack will be specifically pointing to this new context, right? And the context is always top of some stack, right? Okay, and we did this detour just asking ourselves where is that we're switching to. So we were running to the process, and I was saying, okay, so if you think about it, we're switching to the function which was like invoked from the very first main function into which we booted, right? So we said that each CPU, when it finishes booting, starts this MP main function, right? So this is how it looked. Let me just show you for a second. Just trying to quickly scroll through the slides here. So when we booted in main, at the very end of main, we invoke the MP main function. MP stands for multi-processor main, so it will be invoked in every CPU. And inside this MP main function, we ended up invoking the scheduler. And the scheduler is this infinite loop, which essentially says, okay, I will run infinitely here, right? So this is the way to one way to write an infinite loop in C. Say that this for condition doesn't have an exit condition. The for loop doesn't have an exit condition. And essentially, it will be incrementing the value of the pointer, which runs through this process tables. Essentially, x86 maintains all the processes as an array. Each entry in the array is a prog data structure, and this P points to some entry, right? Some of these entries are invalid. And so when x86 starts, it initializes them to some invalid value or inactive, if you like, right? And the process, when the process gets terminated, it gets again back this invalid value. So simplest state, simply the scheduler just skips over all the processes which are not runnable. But if the process is runnable, meaning it's ready to run, right? It will essentially switch the virtual address space, change the state of a process to running, and will invoke the switch function. But this time, instead of like saying, okay, I'm trying to save, I'm switching from my own context. So this time it's a context of the scheduler, right? So we will, in a second, we'll take a look that there will be, on each CPU, there will be a CPU data structure. And this data structure, maybe a better name would be context here, right? At least it will be coherent with the naming. But they called it a scheduler, and they pass a pointer to this field inside the switch function, and this is where we will save the top of the current stack from which we're switching, right? So this stack which is part of the main function, which was created as a part of the main function, and then we're switching to the context of the process we picked from this table. So we picked it here. At some point in the past, remember, we saved something, so we know that this pointer context will be pointing to a top of some stack. And so if we invoke the switch function, that switch function will switch to that stack, and not surprisingly, it will start returning on that stack, right? So this is the CPU data structure, and we'll come back to it like later today. So it's essentially x86 maintains an array of CPUs, right? And identifies CPUs by a number. So CPU 0, for example, is let's say it's a boot CPU. So for now, we talked only about CPU 0, right? But there will be other CPUs initialized, right? And so this is the struct context and a pointer to that context which we maintain on each CPU. So, and then we invoke the same switch function, so everything works the same, right? And what we're doing here is we are returning. So if we are switching from the context of the scheduler, right? So we will save this current stack to the scheduler field of the current CPU data structure. And the second argument which we got into the switch function is a pointer, which is a field inside the process data structure, which we know is pointing to the top of some stack. And not surprisingly, the stack is well formed. So the very top of this stack is the context data structure itself, just 5 fields. Then some functions which call this function, right? So at some point, yield called the scheduler and so on, right? Yield was called by the trap function. So this is the return address. Trap function was called by the all traps. All traps itself saved all the general registers, all the segment registers. Vector32 saved the 0 error code and the interrupt number 32 here. And the interrupt hardware saved 5 things on the stack, right? So logically, if you start returning from switch, right, you will eventually get up to here. And at this point, you can invoke the IRET instruction, right? Agree? So it's almost like you exiting through the same interrupt path, but now you're exiting in a different process. And this is how you switched, right? From one process to another. As long as you maintain those stacks, then everything is fine. This machinery just works. So, and this is what switch starts doing, right? So it's essentially saves the current value of the stack in the, it was called the CPU scheduler field. This is a pointer, right? Which is currently inside the EAX register. And the EDX is the proc pointer context field, right? And we load it in the ESP register. We start returning on that stack, essentially popping values from that stack. The context data structure itself has 5 values. So we pop 4 here, and the ret instruction will pop the 5th, the return address, right? And you will start returning, right? So roughly speaking, this is the context switch. So first time we invoked, like remember, time and interrupt preempted us. We invoked the switch function. We went into the scheduler. Scheduler picks a new process and essentially switches to it again. So it's always like this. So you have some kind of a process, sorry, P1, it's preempted by a timer interrupt, it goes into a scheduler, and scheduler chooses the next process, P2, switches to it, then later on, P2 is preempted, again switches back into the scheduler, and so on, right? It's not optimal, and again, a real kernel might probably try to optimize this step. Instead of switching to a scheduler, it's just possible to just like do the same job, just pick the next process you want to run before calling switch and switch to that other process directly. But x86 does it this way because it's a little bit simpler, less messy, but it's easy to change x86 to choose the next process and just go for it. Good homework exercise, by the way, extra credit. I'll come up with it for you. Okay, let me go to one of those diagrams and we will just quickly discuss where everything gets saved. So, okay, we start returning pro context. I have a bunch of slides here. Let me just again scroll forward because I think we covered it already. Essentially, that's the state of us, the state of the system. So essentially, what we've done here, so we're switching from a scheduler. I cannot spell the scheduler. We're switching to a process P2, right? And so the state of us, the state is like this. So you have a pointer to this field where we're gonna remember the current stack, right? And the second argument is this context, which is pointing like this, right? And so essentially, let's see how we return. So essentially what we do here is we started in a switch function, which cleared this part of the stack. We keep returning trap, all traps, right? So not surprising. At some point we get to all traps, right? What the all trap is doing is that since we push this argument on a stack to call a C function, we free this space, 4 bytes, which we used on the stack. And we essentially fall through here to this trap ret label, which restores all the general registers with a pop all instruction. We already looked at it, right? We looked at this code when we looked at the interrupt pass, right? We restore all the segments. Again, we restore the space, which we use for the trap number and error code. At this point, only the 5 things are on the kernel stack. We invoke the IRAT. It restores these 5 things in registers, and we're back to user level, right? So this is where we are again, but in a different process. So right now it will be P2, right? Agree? Okay. So let me ask a couple of questions. Imagine we were running, before the interrupt, running somewhere here in the user. If I ask you a question, like, imagine you have some kind of a value of the EAX register, right? Where does it get saved to? When we switched away from this process, where do we leave the EAX, the value of the EAX, of the user EAX register? In the kernel stack. Everyone agrees with this? Why? Which part? Where do we save it? So you say somewhere here. Okay, do you remember how it gets saved? Correct. Push all. I forgot exactly how you spell this instruction. Push all saves EAX here. Agree with this. Is that clear to everyone? Right? If we are running, so it's user value of the EAX. What about the kernel value of the EAX? Imagine you already started executing vector 32 and you switched away from this process. So you were running for some time you were running in a kernel, right? So the kernel had this value of EAX, right? So where does it get saved to?
It is more to scheduler or still in kernel?
What's the question?
You said like kernel started executing and it has a value of something in AX, right?
Mm-hmm.
Do you mean that still it is pointing to the user stack of kernel or does it move to scheduler?
No, imagine we entered the switch function, right? At this point, like before we started executing vector 32 and got to switch, AX was probably used by the kernel, right? Do we save this value and where and how? In a where? In the context which we pushed here, right? That's what I would agree with you, but remember, context is only 5 fields, and EAX is not one of them. Why is that? Because EAX is not a wholly safe register. But that's a good guess. So if I change the register name from EAX to whatever, ESI or something, the one of the wholly safe registers, then yes, it will be saved here, right? But EAX is not there. So where is the EAX? Where?
I'm looking at this switch thing. It says move L4 ESP, take the position of ESP EX. They moved into that. So 4 places above the ESI, above the context.
Correct. So at this point, EX is used as a scratch register. So we don't really we only use it temporarily. And we don't care about saving it. But I mean, there is certain truth to it, right? Because EX, if it was used somewhere from the point when vector 32 started running, and by the way, it's not initialized to anything, right? It's just like it's a scratch register. No one cares about the value. If it was used for something usable, then there will be instruction which pushes it. It might not be, so it will push EX and we'll save it somewhere on this stack. So essentially, let me show you a different figure here. So just to make sure that if we have this stack, imagine this is the stack of a process. In this specific example, we're switching to it, but maybe it was saved somewhere here because this get function was using EAX and needs it and it pushed it, or maybe here, or maybe nowhere. So because it's a wholly safe register, but my point here is to just for you to learn to reason about what's going on with those registers, right? The user value we need to save because we have to restore the complete state of the user because user might be preempted right between loading EAX and using it, right? But in the kernel, I mean, it's the same story, but the assumption here that if yield function needs it before it will, so it will be somewhere over here, and then restore it after returning from this invocation, right? Is that clear? This argument. When we invoke a system call, something like cs5460, right? We pass a system call number. How do we pass a system call number? Which register?
EX.
Again, we pass a system call number in the EX register, right? So where is it again? When we are in the kernel, how can we access the value of the system call number if we're executing a system call interrupt? No, imagine you're somewhere inside the trap function. Your register EAX is in some state, but you don't even know in which state, right? Actually, when you enter the function, since it's C, so maybe C does something with this register. Maybe it immediately allocates a local variable in this register instead of locating it on a stack.
Instead of we cannot store on stack also.
So where is it on the stack? How do we access this, the system call number?
We are pushing vectors 0 and 32, right? So where we can add a system call number. We can traverse the stack and we can get the number.
No, hold on. Like I'm asking because x86 is already doing it. So x86, we know that in the user level, right before invoking int x40, which is a syscall, right? The user initialized, moved something into the AIX, which was a number of a sys enter, right? Oh, sorry, sys exec, right? Some number, I don't know what this number is, let's say 15, right? So if we are in the kernel, how do we access this number? In where? In trap frame, because remember, the kernel itself maintains when we invoke the trap function, we pass a data structure, which is called trap frame, and EAX is here pushed by the push all, just exactly like you said before, right? And this EAX corresponds to this number, right? So if you have a location of a trap frame data structure, then you can access it, right? So I don't think it's always accessible. So I mean, I forgot if x86 maintained it. So you can, if you care to have it, so you can add the trap frame pointer here in the prog data structure, which points to this like specific location of the trap frame on the stack, right? On the kernel stack, right? Okay, so what else? And again, so similar logic. So if you want to access the argument which is passed from a user, let me just again scroll forward. If, for example, okay, let me just again switch slide deck. If you are in the interrupt executing a system code, let me just exit the previous slideshow. Start a new one. If you're inside the interrupt, so how do you access this system call argument?
We have an ESP in kernel stack.
Right. So you go again, you use trap frame to use the ESP value. So which ESP value is that? It's a pointer to the user stack. So it's a pointer which points exactly here, right, into the user, right? Agree with this? And then we know that the arguments were passed on the stack, right? And so we essentially do some like, there is a little bit of a, like an extra value there because we invoked yet another function. So there will be a return address, but this is how we access the arguments of a system call, right? So there will be like arg1, and then there will be arg2 and so on, right? Is that clear? So, but again, the point is that when we entered the kernel created this trap frame data structure through a collection of those, like, which starts from the very top of the kernel stack here and like ends here. So it's created by this all trap function and like vector, whatever vector number you have here, and the hardware itself, which pushed these first 5 values, right? So this data structure is a trap frame, right? And when we invoke the trap function, we pass a pointer to the trap frame into the trap function, right? From the assembly to make sure that we can access to all the user registers. So if we want to change the user register, for example, like, why would you like to change the value of the user register? Who can tell me? Who can give me an example? What is a reasonable story for changing a user register? We want to return a value, exactly. So from any system call, you can return a value, right? Because maybe it's an error, maybe it's a success. Even exec or fork, for example, returns ID of a child, right? So this ID of a child, according to the calling convention, will return it in the user EAX value. So essentially what you will do is you will modify trap frame EAX, assigning some kind of a return value here. And this register will be restored and the user will see this value, right? And we'll treat it as a return result from a function, right? Which from a system call, for example, right? Is that clear? Okay, so this concludes our story about the context switch. So any questions?
Can you explain, let's say we have a process P1 containing 3 threads, and each thread, let's say thread 1 is doing like reading data from this, and thread 2 is doing some pipe. So how does it work? I mean, internally, how does it transfer from T1 thread to kernel, and again similarly T2 to kernel?
Right, so we never, x86 doesn't support threads, right? So, and that's your homework, to extend x86 with threads. But the way you can do them, like, there are multiple ways, right? So you can, for example, say something like, you have a proc data structure, and the proc will contain a pointer to the page table, right? Which represents the address space, right, of the process. You say this is all the memory, and for example, you say I will support a list of threads. So for example, it can be a list or it can be an array, for example. And you say this is T0, T1, thread 0, thread 1, thread 2, right? That's just one way to build it, right? And so at every point of time on a CPU, one of the threads is running, right? So it will have its own thread 0 stack here, right, in the user. It will have its own thread 1 stack in the user. And since we can build threads very similar to processes, then you say, look, since I treat, like, I will context switch between threads in a very same manner how I context switch between processes right now. So obviously for that you will have also, if this is user address space and this is a kernel, you will create stacks for each of them. So you will say something like T0 kernel stack and T1 stack in a kernel as well, right? And then you say, for example, since I do remember, so those, I will, in this data structure, you will have a pointer to those stacks, right? Like this. So every time you switch from one thread to another, your TSS will get a value of this kernel stack of an individual thread, right? And what you're going to be doing, since each thread might have a parent process, maybe you will have a back pointer to point to a process itself to make sure that you switch to a correct page table, right? But everything else can remain unchanged, literally. So again, you're running a thread in user level, some instructions, some state on this stack, an interrupt comes. You drop into the kernel, reach the scheduler function. You context switch into the scheduler, right? Scheduler says, okay, instead of just maintaining a list of processes in the system, I will maintain a list of threads in the system. It picks a next thread. This thread might be in the same process or might be in a different process. But no matter what, you will do the context switch in a similar manner, right? So it's one way to build it. There are multiple ways to build threads, but this is one of them. It's called POSIX or kernel threads, essentially, because the kernel does the context switch, right? Any questions about threads? The observation here is that those are contexts of executions, right? T0 and T1, which are sharing the address space. So it's essentially they can access the same memory.
But it will have only one page table.
One page table, right? And
Only the stacks will differ.
Only the stacks and register values will differ, because each stack will be executing its own instruction, will have its own local variable, stuff like that, which might be saved on the stack. There is also a concept of a thread local store, which implements thread local variables. And that's easy to build as well, not super hard. But you see that this is the next homework, essentially. The homework, whatever the number is, 6, will be extending context, extending x86 with threads. So essentially you will come up with those pieces to essentially say, well, I will have another stack. I will have a stack per thread. I will not be like, I mean, most of the context switch can remain unchanged actually. Just the only point is that you have to understand everything, how it works.
What's the size of this array?
Well, it's implementation specific, right? So in x86, I mean, it's up to you. On Linux, it will be dynamically growing. So I don't think it will be limited. Maybe POSIX limits with the constant, but I don't think so. Great. Any other questions? Good. Understood the context switch? Everyone is hoping. We still have half an hour. Okay, good. Context switch is done. So let me now go and switch to this question which I was raising like earlier today. The question of how do we really create the very first process? So again, if I ask you this question, imagine you're an operating system designer. How will you create a first process?
Based on the header, we will allocate pages. Similarly, we are done for reflection.
You can, but maybe there is a simpler way to kind of cheat a little. And I mean, it's implementation specific, and there are multiple ways. But the question is how. Okay, let me show you one way which x86 chooses. So again, remember our main function. By now, we covered almost all of these functions inside main, right? So some of them like initializing the kernel allocator, creating the kernel page table. This one detects other CPUs, so we will cover it next. Initializing the segments, so GDT, global descriptor table, initializing the interrupt vectors or interrupt descriptor table here, right? So at this point, you can re-enable interrupts because before that, you know, if you re-enable interrupts, and remember, we disabled interrupts as the first instruction when we started running, I think inside boot or inside the kernel. And here's this function, user init, which says, okay, we'll create the very first process. Okay, let's take a look how it can be done. So first of all, we'll allocate the process data structure. I keep talking about it, right? So I keep talking that the process is represented with this proc data structure. So let's take a closer look, right? So the way we allocate it is there is this allocproc function, returns a pointer to this data structure. What's inside this allocproc? It allocates this data structure. And remember, I was telling you, if anyone will ever ask you, what is a process on one of the job interviews? If you remember this data structure, you can kind of beat that person to accepting your answer. Because this is one of the shortest ways of describing a process. And you can read many, many books. And like you can be any high up with a philosophy of what process is. It doesn't really matter. So this is intangible terms. This is what a process is. We'll start like from the bottom field. So it has a name. Well, not surprising. Each process will have a name. It has a page table. Again, I told you that the process is an address space, really. It will have a context of execution, right? So at some point, we say, okay, we will remember the context to make sure that we'll come back to this process, right? And there is a context is at top of some kind of a stack. And this stack is a kernel stack. So that's why we have a kernel stack field here, right? The pointer to the kernel stack. So every time we will be switching, and we're sure that there will be no leftover state in the process when we're exiting at the user level. So this kernel stack plus stack size will be loaded in the TSS, right? In order to, again, to tell the hardware where to locate this stack, right? So remember, it will have a trap frame, and this is to access essentially arguments passed from the system calls, values of user registers, and locations of user registers, which are saved on the stack, so that later on you can change them. So essentially, if you say you can always say something proc TF EAX assign like -1, saying the system call returns an error, for example, right? I not. It will have a process ID, right? So we know that the operating system operates with those process IDs. For example, you can kill a process by providing a process ID, right? It will have this runnable state. Remember, the scheduler itself will track the state of the process. Is it ready to run or not, right? So this is the state. Remember, when we create a process, we only load the text, data, guard page, and a stack, right? And that's the entire size of the address space of a process, right? There is no heap yet. So because the process hasn't started running, it hasn't allocated anything on the heap. So the size field is pointing, essentially it's an offset from 0 to the end of this address space. Remember, there is a system call which allows you to allocate memory as BRK, set bracket, right? And this SBRK essentially changes the size by moving it either forward, and the operating system will fill it with pages, or backward if you deallocate the address space, right? So the simplest thing to essentially like how you add heap, right? So you maintain this idea of a parent process. I didn't explain it yet. We'll come back to it later, but essentially the parent can wait on the child, right? So when we forked and we wait, this is when the child finishes, the parent gets notified. That's why you maintain this field, right? We haven't talked about sleeping yet. And this is a field which tells the operating system that the process is killed. We've seen it once when we enter the system call, we check if the process is killed, and if it's killed, we'll just tear it down, right? Two last fields. File descriptor table, remember, it's a pointer to the array of file descriptors. Remember, like 0, 1, 2, 3, standard input, standard output. This is how we maintain it, right? So this proc data structure will have a pointer to this array of file descriptors, right, of specific size, right? To be honest, this is the array. So I don't know, like if I confused it with my wording. So it's array, and each element of this array is a pointer to a file, right? So this is element 0 will point to a file, and that's your standard what? Output or input, I already forgot. This is 1, might point to a console or something like that. Right? Agree with this? And finally, the current directory. We haven't talked about it, but when you type a command, so you can resolve names. Like if you just type a name of a file, foobar, then you say like, where is foobar in file system? So the way you open a file, you say, look, this is the inode of a current directory. And from that directory, I will try to look up the foobar file. We'll cover file systems in next week, essentially. Okay, but that's the process and nothing else. So you don't need much. So again, if you remember the values of these fields, you understand what it is. If you want to run something, if you want to build a tiny operating system which runs on your wristwatch, for example, you can use this data structure. It's pretty much will allow you to build Unix, right? Or subset of a POSIX interface, which x86 implements, which is powerful enough to probably run half of everything what you need. Definitely is enough to run an embedded operating system. Maybe not enough to run GUI, right? Okay, any questions about this proc? Okay, cool. Again, you can read all you want, as long as you understand the meaning of those fields. And again, if you're suddenly uncertain what the field is doing, you can just grab through the x86 source code and figure out what the field is intended to do. You will find it reasonably easy as long as you read the source code. Okay, so x86 has predefined, it has array of proc data structures, right? And alloc proc just picks the next available entry in this array, right? And returns it as a P. P is a pointer to this, right? Okay. Since proc has a page table, we definitely need to create a page table for the process. We first create only the kernel part of the address space, and we use one of those functions which we've seen before, set up kernel virtual memory, set up KVM. And it returns a page directory, right? might panic here, and at this point, you know, we run out of memory, so that we don't know what to do at this point. The kernel halts. So supposedly should want to work, right? But at this point, you know, you somewhat ready to run a process, right? But as you say, you created the page table. You need a little bit of pages for the user for the text and data sections, right? Okay, so we're gonna do that. So there is this function which we implemented, init user virtual memory. We also seen it, right? So it takes a page table and it just says, okay, remember init UVM, load UVM, which we used inside the exec. Init UVM says, okay, you give me the start address and the end address or the size, and I will allocate enough pages to cover this region. So this is exactly what this function is doing here. Okay, it says, okay, I will allocate this memory and we'll map this pages, right? It's essentially, right? So we've seen it before. However, no, we actually haven't seen this. So init UVM is a new function. So it actually allocates, it's a shortcut. So it will allocate only one page. So it says, okay, if suddenly you want to allocate more than a page size, we'll panic. But what we do here, we allocate one page, we map this page in a page table, we map it as writable and user accessible, and then we copy the content of this page into this new memory which we allocated. The trick here is, what is that we're copying? We're copying some magical values, binary init code start and binary init, and the size of it is binary init code size. So those guys are declared as extern, which kind of provides us a hint that it's what? What can be those things? Like, especially this name start is suspicious. Constructor for initialization. Any other ideas? What can we put there? What do we really want to put in the user? Like, okay, conceptually, we're creating maybe text in a data section for this init process. By the way, we're cheating here and we say those two need to fit in one page. But what is it we want to put here in this text section? What do you think is the most convenient thing to put there if we want this first process to do something meaningful? Invoke shell. How? I agree. That's the right direction, because we want shell. We want to boot into shell. So at some point we want to see the shell running, right? But how do we start the shell? You have it.
Is the init code meant to be like a filter or some sort of thing where you will know what the shell is, where it's
Correct. But more concretely, how would you do this? What's the easiest way? I mean, that's the right line of thinking. Like, we want to get to shell from this init code, but how? How will we get to shell? What is shell? Just again.
load shell program.
The question: can you load a shell? I agree. Can you? How? What's the easiest way to load the shell? As a process. Agree. So how? Do we have machinery which allows us to load shell? What? Like a loader, elf loader? We can, but do we really need to build yet another elf loader? Maybe we already have one. Because we had one, we actually discussed it. I mean, this is all valid. So you can build an elf loader, but maybe you don't need to. So I suggest to go with the simplest possible approach. Exactly. Why not? So look, we have system calls. Shelf is the binary in the file system. Exec already nicely supports loading binaries from file systems into memory. So if inside your init code, you can implement exec passing shell as an argument, you seem to be golden. Why not? It's valid, right? So the threading system already can exec into shell, right? So that's exactly what init is doing, besides the fact that init, instead of starting shell, it starts a special process which is called init. And it's done for the reason that it has slightly different logic, because shell can exit. And then init, which on a normal system would probably, will ask you for login, right? Or like init can start a logging shell first, which says, okay, type your username, a Burtsov, type your password, I type the password, this goes into the file system, checks the passwords file, compares them, compares the caches, says yes, and then starts a shell for me. But this guy essentially will do, we'll take a look at the code, but it will start shell infinitely. So essentially in x86, if you exit from a shell, you exit into init, and init will immediately start a new shell. So that's why you cannot really exit from x86, right? But this is essentially what you're doing. You say, okay, I will have a tiny sequence of assembly which invokes the syscall interrupt. So sysexec will be my argument because I'm invoking exec system call. So I will fake this return address because normally there's a slightly different, it expects this layout of the stack, so I will push just a dummy value. But I will do like just essentially 2 arguments on the stack. The init string itself, because it has to be like, and it starts with this slash, right, for full file path, right? So starting from the root. And the arguments are this array of argv, which is the name of a process itself. And by the way, someone was saying, do we have the 0 for this array? Apparently x86 still expects to have a 0, right? So that's essentially, so this argv is an array, declare it as a name of a process and no argument itself, right? So this thing will successfully invoke the exec system call. Exec will create this process. By the way, nothing is running yet, so it will be just created, right? So there will be, by the way, exec doesn't use a new proc data structure. It will just replace the memory of this one, right? It will reuse the same proc data structure, just replace the memory, which is currently this init code, with the memory of the init process, right? And what the init will be doing, I mean, I will show you what init will be doing, but okay, if we load this code in memory, right? So we load this code in this page which we allocated, and we said that this will contain a text and a data section. We don't need to care about the stack because like the stack is also baked here because those arguments, like the init string is created by the compiler, will just correctly set up ESP to point to them, right? So that's fine. So everything, text, data, and stack fit on one page because we know that it's tiny, so it will fit. We need to make sure that when the scheduler switches to this process with the switch function, the context or the kernel stack of this process is correctly configured, right? Because we want to make sure that, you know, like we can exit into this process, right, and start running at user level. So we have to correctly configure the trap frame for the IRAD. And that's what we're doing. Essentially, what we do here, we say, look, the process will maintain this field trap frame, right? The scheduler will switch to it. And what we will do, we will first allocate the kernel stack for this process, right? We still say that the process is not runnable yet. It's unused, right? But what we do is that we configure correctly the stack value, which is the kernel stack page plus the stack size. And then we start reserving space on the stack saying, okay, decrement the stack pointer by the size of the trap frame, right? Because that's exactly what we want to have on a stack. And essentially what we do here, we correctly configure this trap frame. So we configure since this process never ran, so the state was never saved by the old traps and stuff like that, we will just make up these values on the trap frame. So we will correctly set the code segment, which is a user code with a privilege level user, data segment, again, user data with privilege level user, ELs and SS are the same, E flags, just whatever, interrupts are enabled. The location of the stack is the page size at the very top of that page, why not? EAP, we know that essentially init code is linked to be at the beginning of that page. So just set the EAP to 0, that's okay. This is when we start returning. That's what when IRET will restore this value, it will correctly set up the user value of the instruction pointer at the user level to be pointing to 0, right? Okay, cool. So at this point, we will configure this trap frame, and then we say like the name of this process is init code. Current directory is name_i is a function which opens an inode by the pass, essentially. Remember, we looked at it when we did the exec. And at this point, we can say the state is runnable. So if the scheduler will find this process later on, it will happily switch to it and run. And at this point, you say the scheduler says, okay, the top of the stack is some context. So we have to be careful. And maybe I skip a couple of lines here, which essentially just make sure that we put the context on the stack as well. But that's what we do as well here. And at this point, the switch function will correctly, like we pass this, essentially what we will do something like proc context will be pointer to this top of the stack, and then we will switch to this process later on. So that's how the very first process is created. If you ask me a question, what is this process doing? So that's exactly the logic of this init process. So remember, the shell needs a couple of things to run correctly. Someone has to open the file descriptors for the shell, 0, 1, and 2, right? That's a POSIX convention. So that's exactly what we're doing here. So we check here if we actually can open there is a special file in a file system, which is called a console. If it doesn't exist, we create it as a device, right? So it's a little bit of a magic here, and then open it, right? And then we duplicate it twice. Remember, dup takes the number of a file descriptor which we are duplicating and picks the first unused entry in the file descriptor table. Since the file descriptor table at this point has only one entry, 0, since we just invoke open once, right? So 0 is initialized to the console, and dup essentially duplicates the console twice. At this point, the shell, if you fork into the shell will have these values and will correctly use file descriptor 0, 1, and 2, and everything will show up on the context, right? On the console, sorry. At this point, you say, look, it will be running in an infinite loop. It's again implementation specific, and you essentially fork. You first print says, okay, I'm starting init. You fork and exec into shell, right? And at some point, if like in a parent, you start waiting on this shell, and if the shell returns, you continue and will fork the shell again, right? So if I run x with 6, let me just do it very quickly. So if I boot into the x with 6, okay, sorry, it will build. So it printed this init. I have some debug output here, which is probably from one of the homeworks, but it says init starting shell. I'm inside the shell. I can do ls. It already connected to the console. If I do exit, if I do control, so do I have kill? If I kill 0, for example, do I have PS? PS failed. So I wanted to, I forgot in my homework, do I ask you to implement to dump the list of processes in the system? I probably don't, right? Okay, so I used to in the previous year. So if you can guess the shell, init exiting. So okay, so my interpretation probably of the source code was incorrect. So essentially, why did it panic? Okay, I don't know why it panicked, but to say my idea was that it shall not panic. And so if you kill the because sorry, I accidentally killed init instead of shell. Okay, let me do again. Sorry for this demo. Let me kill process number 2. So if I kill shell, which is 2, I believe, so it essentially exits into the init and starts the shell again, right? So I would assume that if I can kill 2 again, no, so it picked a different PID for the process. So let's say 3. No, which one then? I don't know which one. It allocproc essentially allocated some process number. Right? Okay, so that's the idea. So you start init, and Linux works very similarly. So it also has an init process which has a similar role, right? Okay, any questions about this? All good. So we understood, like at this point, we almost understood the boot sequence and kernel initialization and most of the kernel machinery. So all the parts are initialized. I will only cover what I will do next time. So because it's too late today, I will explain how the system initializes other CPUs and really what it means to run 2 CPUs simultaneously and what synchronization primitives we need to synchronize between them. So it's a lecture on synchronization, and we will cover spin locks essentially, right? Okay, but essentially at this point, yeah, you know a fair bit. And so the only topic which we will cover after that, which will be next week, will be file system, right? And then after that, you're ready to build your own operating system. Okay, any questions? All good? Okay, thank you then. See you Thursday. I will assign the quiz still. I will. Quiz will help you to go through the next homework. Thank you.